Okay, let's start. Thank you very much for being here. Thank you to our speaker, Benedetta. She did her master PhD studies in Padova. And then she moved a little bit around the world to Qatar, Tokyo, Melbourne, and then finally back to Padova. And today she's going to give us a talk about galaxies under pressure. So,
Thank you.
Thank you very much.
Good morning, everybody. It's really a pleasure to be here today. And in this talk, I want to show you some results about the importance of the environment in affecting galaxy properties. And just to be clear, in this talk, I will just focus on galaxies in the local universe. Otherwise, I could stay here forever. So, we know that galaxies are not distributed randomly in the universe. They really follow a net in the cosmic web that is actually the distribution of dark matter. So, in general, we can find some galaxies that are found in the field in average density. And these galaxies are typically expected to evolve only due to internal mechanisms. So, they don't have much influence from the surrounding regions. But then we can have galaxies which are found in filaments that are with this long elongation. And this is a kind of a new environment in the sense that only in the latest years we have started really to understand the impact on filaments in galaxy evolution. And we think that this is really the first environment that galaxies can enter into feeling some external density. These filaments typically connect these bright nodes in the cosmic web. And depending on the size of these nodes, we can have either galaxy groups, which have small association of objects, or galaxy clusters, which are really the biggest realized regions in the universe. Then, if we go back on the other side, actually we also have some galaxies that are really in voids, that are really in some empty space where there are no other galaxies. And in the latest years, it's been shown that also galaxies in voids can have an evolution which is different from the galaxies in the general field. So, before going into the results, I just wanted to highlight a little bit of every different environment. So, as I said, galaxy clusters are really the most massive relaxed systems which are known in the universe. And in the local universe, most of the galaxies in galaxy clusters are passive, red, and ellipticals. And this was really the first hint back in the 80s, I think, that people understood that environments must play a role, because galaxies in the field, on the other hand, are typically star-forming, blue, of a late-type morphology. Another important thing is clusters are open boxes. They continuously have an inflow of new galaxies. And in this plot, you can see how galaxies can fall into the clusters. Each galaxy can have a very different path. We can have galaxies that fall directly onto the cluster. This infall can happen early on. It can happen very late in the age of the universe. Galaxies can fall first in a group and then fall into the clusters. We can have clusters that merge with other clusters, and groups that join the clusters early on, later on. So, trying to understand the environmental history of the galaxies is something that we still are trying to do. And we still are trying to understand if we can see signatures of this so-called pre-processing, meaning what happens to the galaxies before they enter into the cluster. So, clusters continuously accrete new material, with the results that clusters themselves evolve with time. So, overall, from high redshift to low redshift, the halo mass of the cluster increases. Clusters become bigger. But this is a little bit counterintuitive. But galaxy clusters at high redshift, they were denser than today. So the clusters actually become less dense as we go from high to low redshift. What happens when the galaxy enters the clusters? Overall, they feel the cluster potential and stop forming new stars. And in this plot, you have the fraction of quenched galaxies as a function of the time since their inflow. And let's just focus on the solid line, and we see that the fraction of galaxies, the quenched galaxies, increases with increasing inflow time. So galaxies that have been in the clusters, that fell into the cluster earlier on, have a higher probability of being quenched than galaxies that just enter into the cluster. So there must be a process that quenches the galaxies. Then we have galaxy groups, that are actually the smallest aggregates of galaxies. To some extent, groups can be considered a small scale of clusters, but there are some critical differences. Well, typically the groups contain only up to 50 galaxies, where clusters can contain up to thousands of galaxies. Their mass is typically 10 to the 13. Galaxy cluster can reach up to 10 to the 15 solar masses. Clusters groups are the most common structure in the universe. It's really the most typical environment in which galaxies can be found. But with respect to the clusters, groups are typically young, they are still collapsing, assembling, they are not very alive. So this is a young environment. And only recently we have found some groups that host also an X-ray, suggesting that these groups are permeated by an intergroup medium that emit at X-rays. But not all the groups have an X-ray. And finally, we can go to the filaments that are really the largest known structure in the universe. Here there is just a plot showing the filaments that we identified around the Virgo clusters. And you can really see that they elongate up to many degrees in the sky. There are many theoretical works that show that there are well-defined scaling relations that connect the length of the filaments, their mass, the gas contents. And we know that the filaments can extend up to 200 megaparsecs. So these structures are really huge in the universe. Densities in filaments are intermediate between the clusters and the film. And here you have the distribution of the local density, and you really see how filaments are intermediate, suggesting that this is indeed the first time galaxies can fill a higher density, so we can expect some variation in their galaxy properties. Filaments really are this big highway that help galaxies to fall into the clusters. As we have seen in the picture before, filaments really connect galaxy clusters and groups, so they really help galaxies to fall into the densest node of the cosmic web. With respect to clusters and groups, a problem of the filament is that the detection of the filaments strongly depends on the method that we use. There are still many methods, and even on the tracer. With the PhD students in Padova, we have characterized with simulation the filaments in semi-analytic models using galaxies as tracers and dark matter as tracers. In observation, galaxies is the easiest thing we have for selecting the filaments. And we have seen that overall, galaxies tracks quite well the dark matter filaments, even though there are some discrepancies. Another important thing to consider is that in the same region of the simulation, if we use galaxies of different masses, from 10 to the 7 to 10 to the 8 to 10 to the 10 solar masses, we can get quite different filament structure. And this is because only the most massive galaxies really trace the filaments. The low mass galaxies are distributed more sparsely in the universe. So studies that characterize filaments always need to keep in mind when comparing to other studies what is the method, what is the tracer, and how the filaments have been identified. And then just a couple of words on the voids. This is the only slides on voids because I don't work on voids. So these are really the underdense regions in the cosmic web. And really, even though there are very few galaxies, they occupy up to 80% of the total volume in the universe. The sizes are typically between 10 to 100 megaparsec, and the number densities are very low. It's less than 20% of the typical densities. Voids are typically surrounded by filaments and walls that really contains this space. And this is really a unique laboratory to study very underdense regions. And overall, there are some studies that show, for example, that in voids we have a larger fraction of spiral galaxies with respect to galaxies in the field. And so this is a suggestion that even these underdense regions have an impact on galaxy evolution. And nowadays there are many results from the cavity survey that are really showing what is the role of the voids in galaxy evolution. So I mentioned that galaxies can change their properties in the different environment, but why is this? This is because there are many different physical mechanisms that affect galaxies, and these mechanisms are called environmental processes. And this is because they really depend on, or are more effective in different environments. This is just a list of the different mechanisms that people typically invoke, but the important thing is that we have to keep in mind that we can divide these mechanisms into two big families. On one side, there are the gravitational mechanisms that are, for example, mergers, tidal interactions that involve and affect both the stellar components and the gas components in galaxies. And on the other hand, we have the family of the hydrodynamical mechanisms. And these are run-pressure stripping, harassment, starvation, and these only affect the gas. Stars do not care about hydrodynamical mechanisms. And this is very important when, as I will show you in the rest of the talk, we want to characterize the physical mechanism. And as I said, these are environmental processes. In this paper that of 2003 from Treo et al., there is this plot where they show where the different mechanisms typically happen as a function of a hypothetical cluster center. So we have the mechanisms like run-pressure stripping typically happens in the cluster cores. You really need to have hot, dense intercluster. On the other hand, mergers typically do not happen close to the clusters and in the clusters, and this is because the relative velocities of galaxies in the clusters are too high, so the galaxies don't see each other and they can merge. On the other hand, mergers typically happens at the group levels in the field. So, depending on where the galaxy is, we can expect what mechanisms to be more effective or less effective. Even though, and this is a spoiler of the very end of the talk, we still don't have a clear picture of a clear census and an incidence of the different mechanisms in the different environment. And this is something I will tell you about next time, I believe. So, the main question is, what is the evidence of the different physical mechanisms that act on galaxies? When a galaxy enters a new environment, the first thing that is affected is the gas component, and more specifically, the H1, which is the least bound component. And so a way to see whether there is an effect on the galaxy is by studying the H1 deficiency. That is a parameter that tells us the difference between the H1 content we measure in a galaxy and the H1 content we would expect if the same galaxy were in the field, and so galaxies of similar morphology and similar size, similar mass, as if it's in the field. And already in the 70s, they showed that the H1 deficient fraction depends on the cluster size. This is the X-ray luminosities, more massive clusters are here. And we have a clear H1 deficient fraction increase from the smaller clusters to the most massive systems. So in clusters, H1 gets easily stripped. And also, if we measure the H1 deficiency as a function of the cluster-centric distance, we see that galaxies in the core of the clusters are more H1 deficient than galaxies in the external regions. And so we see that typically in clusters, galaxies do not have enough H1. What does it mean? They stop forming stars. They don't have the fuel for star formation. There are two different channels to remove the gas. First of all, we have a slow gas removal channel. And this gas removal suppresses star formation. How we can characterize this? By studying the star formation rate mass relation in clusters in black and in purple in the field. And this is for some local clusters from the omega wind side. And we see that clusters and field actually share a similar main sequence. Galaxies in clusters can be as star-forming as galaxies in the field. But we see a population of galaxies that is below the main sequence. And these galaxies are called in transition. And this is a suggestion that the suppression of star formation must act on long time scales. If the suppression of star formation was quick, we would see the galaxies jump from here to the passive sequence. So we wouldn't see this population. We can look where this population is in at different cluster-centric distances, and we see that we really need to get to the cluster cores within the half of the Wheeler radius to really see the emergence of this population. So galaxies really need to get to the cluster core, or they need a delayed time, where they need some time before realizing they are in a cluster. And something similar can be found even at redshift 0.6 up to redshift 1.5. So we see this population of galaxies that are in transition. Something similar can be found also at the group level. Here we have again the star formation rate and acceleration for galaxies in groups in red, and we see that with respect to the field, we have a slight decrease in the star formation rate and acceleration. So we have galaxies in transition in many different environments. And the transition, the fraction of these galaxies in transition does depend on the environment. And we see this even at the okay, now, but there are also some works that actually do not find this, probably suggesting that the selection function of the samples actually has a role. But we see this also in filaments. This is a work on the filaments around Virgo, and we see when we compare the galaxies in filaments with isolated system, we see again that we see this population of galaxies below the main sequence. So even at the filament level, we see hints of this population that starts losing gas and so starts suppressing their star formation. In another work, we try to characterize better the time scale of this, and we follow a prescription from Wetzel et al., according to which, when a galaxy enters in a cluster, there is a delay time during which the galaxy doesn't realize it's in the cluster. So it forms stars at the same rate as usual. And then there is a quenching time, and during which the galaxy quenches. And so we run some models trying to vary the delay time and the quench time for galaxies that enter in the field, and then we compare this star formation rate with observed star formation rate in clusters. And so we see that actually the model allows us either to have long delay timescale, but very short quenching timescales. And this is consistent with Ramp-Ratio stripping, or very short delay time and very long quenching time. So looking at this, we can have a very short of this phase and a very long quench phase, or we have that the galaxy for a very long time doesn't feel the environment, and then very quickly it quenches. If we look at the colors of these galaxies, and here we have the star formation rate and acceleration color-coded by the age of the galaxy, or the color is the same, we see that the transition is very, very small. We don't have a jump into the distribution, suggesting that the transition must be very small. We have galaxies of all ages in the clusters. And so this suggests that actually starvation is the most favorable scenario. However, all of these studies actually use integrated properties. So we are doing studies on a statistical level. Overall, we see correlation, but we cannot really pinpoint the exact mechanism. To do this, we need IFU data. Spatially resolved data, indeed, are really the key to infer the mechanisms. Let's assume we have this galaxy, and with integrated values, we just assign one value of mass, one value of star formation to this galaxy. But it's very clear that there are spirals, there are clumps, there are star-forming regions. And if we just put a fiber on this galaxy, we just get an average of this. And actually, if we are lucky, we have the entire value. But we can have a smaller fiber, we can have a slit. And so we have a biased view of the galaxy. But with the advent of IFU, we can really map the entire galaxy and really have a spectrum at each position of the galaxy. And we can really compare what's going on in the different portions of the galaxies. So when we use IFU, we work with data cubes. So we can imagine to have either a spectrum at each position of the galaxy, or we have a huge amount of monochromatic images of the same galaxies. And we can really infer many different properties. The most known, most used instrument nowadays that provides IFU data is MUSE on VLT, which has a capability of a very large field of view of 1'. And so in the local universe, with just one pointing, we can have the entire galaxy without having to mosaic. MUSE have a very large width range in the optical, so we can get all the emission lines that we need to infer star formation rate, metallicities, ages, so on and so forth. And it gives us about 100,000 spectra per exposure. So the richness of MUSE is really incredible. So we can observe galaxies with MUSE. And going back to the starvation that I was talking about, here there is an example of a galaxy that, thanks to the IFU, we can establish its starvation. I will talk later on about the sample that this galaxy comes from, but let's start with this. So this is a passive galaxy. We see from the spectrum that is passive, it has h beta or 3 in absorption. Its stellar velocity field that tells us how the stars move in the galaxy, it's very regular. So there is no indication that there were gravitational mechanisms. And here we have 3 plots that compare the star formation history in 3 different ages. So with spectrophotometric model, we can quantify the amount of star formation there was at different epochs. And overall, at the different epochs, the extent of the star formation was very similar. This means that the star formation was suppressed in the same way throughout the entire galaxy life. And this is an indication that starvation is going on, because starvation removes the fuel for star formation, the galaxy just consumes the gas that it has, and this happens in a smooth way throughout the disk. So this is a case for starvation. And in general, some other evidence of starvation is that in groups and clusters, the mass metallicity relation is systematically higher with respect to the field. And this is because as the galaxy enters the cluster, it loses the gas. And also it does not have any new inflow of a low metallicity gas. So it just uses the gas that it has, and we have an increase in the metallicity at the medium and stellar mass. And also with starvation, we can explain the fraction of the red spiral galaxies. These are galaxies which are passive, but they didn't change their morphology. And this is because they simply consume the gas they have without having strong morphological variation. This, though, is only one channel for removing the gas. The other channel is a fast mechanism. And this is very well represented by the K+A or post-starbust galaxies. These galaxies are characterized by strong Balmer line in absorption, no emission, and their spectra is a combination of A-type stars and K-type star spectrum. And this is really a great clock to understand when the star formation was interrupted. And we know that star formation has to be truncated in the last gigayear. So when we see a post-starbust spectrum, we know that the removal of the gas had to be quick. Post-starbust galaxies have been studied both in the field, in groups, in different environments, and in clusters. And overall, the properties of the post-starbust galaxies are very similar in our environment. But the incidence of post-starbust galaxies strongly depends on the environment. Here we have the fraction of post-starbust galaxies as a function of halo mass. And we see that there is a clear increase. So, cluster, more massive systems are very efficient in producing post-starbust galaxies. While, even though there are post-starbust galaxies in the field and among isolated galaxies, this fraction is very small. And this is true both in the local universe and also at higher redshift. This is a redshift about 1, and we really see that the fraction of post-starbust galaxies increases as we go, increases in the clusters with respect to the field, that is the purple line. Overall, we think that the post-starbust phenomenon actually is produced by different mechanisms in the different environments. Indeed, in the field, it's mainly due to merger or AGN feedback, while in cluster, we expect it's related to run pressure stripping. And so again, we can go into some IFU data and see whether we see some signature of run pressure stripping. And here, it's again a sample of galaxies that we observe with MUSE. We have the integrated spectra, and we see we have strong H beta in absorption. There is no HRT emission. These galaxies are passive. And when we start the star formation history in 4 different HBs, we see the galaxies today are all passive. There is no star formation. But we see, and it's mostly clear here, that the suppression of star formation was outside in. The galaxy loses its star formation in the outskirts and then in the center. And this is a clear signature of run pressure stripping that really removes the gas from the external part of the galaxy to the inside. And we'll come back on this later. So in general, I showed you that gas is lost. And in general, there are many consequences of this quenching. And just to close this part, we know, for example, that there is an increase in quench fraction. Here we see that both at the cluster and at the group level, we have an increase of the quench fraction as we go from the low massive halos to the most massive halos, also depending on the stellar mass of the system. Then we also have an increase in colors. Galaxies tend to become red, and we have a higher fraction of red galaxies as we move from the least massive system to the most massive system. And in the filaments, there is also a clear trend that says that galaxies that are closer to the filament centers are redder than galaxies that are in the stellar region. And again, this is an indication that galaxies are quenching. Another result is the morphological mix. If we study the morphology density relation, we see that in clusters that have highest densities, the fraction of elliptical galaxies is higher than in the less dense regions. And instead, late-type galaxies are typically found in the least dense environment. And this is not true only in clusters, but there is evidence also in groups and in filaments that the morphological fraction do depend on the environment. So now I just want to focus a little bit more on RAM pressure stripping. I talked about RAM pressure stripping, but I haven't said actually what it is and how it actually works. So this is a video that really shows what's going on. Here there is a galaxy that enters the clusters, it's a spiral galaxy, and you see that with time it developed these tails. And these tails are due to the fact that when the galaxy enters the medium, if the medium is dense enough and the galaxy is moving fast enough, it's not able to retain anymore its gas. So the gas is lost, and so it's lost behind the galaxy as it moves. So this is the RAM pressure stripping. And the RAM pressure stripping depends, as I said, from the density of the medium and the velocity of the galaxies. Where does RAM pressure stripping typically happen? In these regions of the phase space. The phase space connects the position of the galaxy within the cluster and its velocity with respect to the velocity dispersion of the cluster. And galaxies that are located in these regions typically are subject to RAM pressure stripping. So the galaxy must be very close to the cluster center and move very fast. In this case, we have RAM pressure stripping. Observationally, there are many ways to detect RAM pressure stripping. Let's call them candidates because we haven't confirmed it's indeed RAM pressure stripping. And the different wavelengths that we use tells us something different about the evolutionary phase. If we select galaxies, for example, in H1, we are sensitive to the initial phase of stripping. As I said before, H1 is the first component that gets removed. So we really see the very initial part of the RAM pressure. When we look, for example, at H-alpha narrowband images or optical spectroscopy, we are capturing a later phase because we already have to have stars in this strip tail. So we have to give some time to the galaxy to form stars in the tails that then ionize the gas, and we can see the emission lines in the optical images. If we look at broadband or UV images, actually, again, we are sensitive to galaxies that have already star formation in the tails, and the time scale is a little bit even longer because the time scale of star formation of the UV is longer than the H-alpha, for example. Then we can detect the RAM pressure stripping country in X-ray, and so we are really sensitive to the high density and low temperatures of the gas that is compressed by the shock with the intercluster medium. And finally, we can also detect galaxies with low far at radio wavelengths, and this is even a final phase because we need to give time to the supernovae to explode, and so we see the acceleration of the cosmic rays that emit in synchronous emission. So each of these ways are very powerful to detect RAM pressure stripping galaxies, but it's always important to keep in mind that samples might give different results because actually we are looking at different things. But in other cases, we expect to see long tails of material behind the galaxy. This is not the only morphological feature of RAM pressure stripped galaxies because we can also have unwinding galaxies. RAM pressure tends to open up the arms of the galaxies as they fall with given inclination into the cluster. But unwinding galaxies actually are sometimes also due to mergers. So now, with the postdoc in Padova, we are trying to characterize how often RAM pressure stripping produces the unwinding system and how often actually is merger producing the unwinding system. So with the idea of really characterize RAM pressure stripped galaxies, we studied this project that is called GAPS. We observe 94 stripping candidates in local galaxies, in local clusters, and in some galaxies in the field. And then we have a sample of undisturbed galaxies. Thanks to the big area coverage of news with just one pointing, we have the entire galaxy, and we try to map a wide range of stellar masses. So we had all these galaxies that are candidates of stripping. We see some tails, but we don't know if these tails are really due to Raman stripping. We try to exclude mergers because we really want to look at the hydrodynamical mechanism. We started with the optical news VLT data, but then we are collecting a wide range of data from ALMA, H1, UV, HST, X-ray, to really have a comprehensive view. But today, I will just continue focusing on the news data and so optical spectroscopy. So these are some of the galaxies that we observe. This is a RGB image, and when we look at the same galaxies in H alpha, this is what we say. We really see this long tails of material of H alpha emission that is displaced. And the biggest question is to really understand if this is Raman pressure and what is the effect of these tails on the galaxy life. So to confirm these Raman pressure stripping candidates are indeed undergoing Raman pressure stripping, first we need to establish if they are member or not. So we establish if they are member of a massive system. Then we looked for the young tails, and the tails must be young. The galaxy before entering the cluster is a normal spiral. When it enters the cluster, it starts developing these tails. So here we have an example, maybe that you can see it very well, but here it's an example of an HST image where we see the tail. And here it's again the star formation history of a galaxy. We see that the galaxy was very regular at the beginning, and then it starts developing this tail. And this is an indication that the tail is young and is consistent with the time the galaxy entered the cluster. And the other important part is that we compare the gas kinematic and the stellar kinematic. Raman pressure is an hydrodynamical mechanism, so stars do not care about Raman pressure. They keep rotating smoothly and regularly. Instead, the gas is disturbed, so the gas is removed, but it maintains the coherence of the stars. So this is an indication that this gas was part of the galaxy. It's not gas that fell into the galaxy at some point. But let's focus on this plot once more. And an interesting part is that when you compare this, you see that in both cases there is a tail. But you can notice that here there is star formation on this part, and here there's no more star formation. So we see a signature of quenching. If we look at the spectra here, these are typically post-alpha spectra. So the galaxy is still producing stars, but Raman pressure is eating up the gas outside in. It's removing the gas from this side of the galaxy, and we see post-alpha signal. Another interesting difference between these two plots is that here we have an enhancement in star formation. Indeed, Raman pressure not only removes the gas, but at first it compresses the gas, so it boosts the star formation in the center. If we look at the star formation rate and acceleration, both in the local universe and also at intermediate redshift of galaxy in undisturbed in black and in colors undergoing Raman pressure stripping, we see that there is a systematic enhancement. So Raman pressure stripping enhances the star formation before leading the galaxy to quenching. And this is seen also on special scales. So we have these samples of candidates that we selected for being disturbed and thinking whether they were Raman pressure stripping or not. We observed them with news, and then we were at the point of comparing our initial classification that was based on the B-band images. And it was really by looking at the images and saying, okay, I think that this is a Raman pressure or not, with an analysis from the news data. And we characterize the galaxy according to a scheme that gives us the strength of Raman pressure. And then we can compare our initial classification based on B-band optical images with our new classification. Here, J-class 5 are the strongest cases. Here, J-type 2 cases are the strongest. And we see that there is quite a good correlation. So optical images actually is good enough to identify Raman pressure stripping galaxies in clusters. It's interesting though that many galaxies that now are J-type 2, so meaning that they have very long tails, actually were J-class 1 in B-band optical images. So the B-band images actually undermine and underrepresent the strength of the tail. And this is just an example. This was a galaxy where we might see something here. So it was J+1. We went to the RGB, we went to H alpha, and you can really see the tail. So it's very important, even though with big-band images you can detect the galaxies, you can really unveil much more in using optical spectroscopy. But overall, in 80% of the cases, we were able to confirm its RAM pressure splitting. So this is very high success rate in clusters. So from this number, we can try to figure out what is, in general, the importance of RAM pressure stripping in clusters. So we had a big sample of galaxy clusters, and we visually inspected all the galaxies, and we selected the stripping candidates based only on the big-band images. Then we selected galaxies that are blue, bright, late type, that are part of the clusters, and we simply compare here in this region the fraction of galaxies that show disturbances with the fraction of galaxies which are blue but which are undisturbed. And we see that almost 30% of this blue population actually show sign of stripping. And typically the candidates are brighter, bluer, and more massive than galaxies that are undisturbed. And if we make some assumption on the duration of the tail visibility, of how long the galaxy stay blue, we can infer that almost all blue galaxies undergo a RAM pressure stripping event during their life. So this means that at least in the local universe, RAM pressure stripping is by far the most important mechanisms affecting the properties of the galaxy. What about the other environments? So with gas, we also have some galaxies in groups, and in this group, we observe 4 different galaxies. And here, in 2 cases, we see signs of RAM pressure. So again, also RAM pressure actually in some cases can act also in group. These 2 galaxies, though, are very different. In this case, this galaxy is at an initial phase. We really see just the beginning of a tail. While here, we see a truncated disk. Here, the gas has been already eaten up. So even the same group can host galaxies at different stages of RAM pressure splitting. And again, then we have another galaxy that instead underwent starvation. Again, the galaxy is passive, there is no H alpha emission, the stellar kinematics is very regular. If we look at the star formation history in 3 different age beams, we see again that it went down in the same way at all distances from the center. So the gas was removed systematically at all distances consistent with starvation. But interesting, thanks to gas, we also have some cases of gas accretion. This is another galaxy in the same group, and we see here the stellar and the gas kinematic, and we see that the gas is much more extended than the stellar kinematics. And indeed, in the star formation history, we see that the galaxy acquired about 1 year ago some gas. There is a boost in star formation, in the extent of the star formation, only 1 year ago. And the other interesting thing is that in this case, the gas is counter-rotating with respect to the stellar component. So the gas was injected in the opposite direction, and so we have a counter-rotating disk. Thanks to gas, though, we also characterize some galaxies in filament. And here we saw something peculiar. These are the only galaxies that were in filaments, and these are all characterized by a very patterned H alpha distribution, which is very regular. There is no clear tail. But these are the galaxies with a more extended H alpha disk with respect to their effective rate. And so this is an indication actually that in the filaments something might happen. If we look again at the star formation distance of these galaxies, we see that this pattern distribution occurred only in the last 10 to 8 years ago. So this is an indication that probably when the galaxies entered into the filaments, again, something happened. And we see that what happened is that the galaxy passed through the filaments. There is the density of the filaments induced a collapse of the densest regions in the circumgalactic gas of the galaxies, and so the filaments really assist gas cooling. But the problem is that this is just our idea, and we really need some theoretical support so far. So, thanks to gas, don't be scared, I'm not going through this all, but we developed the scheme based on a diagram that based on the different IFU properties and the knowledge of the environment, we can identify galaxies undergoing starvation, pressure stripping, cosmic wave enhancement, gas accretion. And we also have some galaxy-galaxy interaction and merging. And this is very interesting because we try to avoid in the initial selection, gravitational mechanisms. But in the field, we actually found quite many cases of merger and interaction. This is the distribution of the different galaxies, of the different classifications that we have, and we really see that mergers and interaction are quite abundant in our field sample. So the visual selection that works so well in clusters to identify ramp pressure stripping, it doesn't work at all in the field. In the field, it's much more difficult to understand what is the physical mechanisms. So we can't actually assess what's going on. The other problem of GASP is that we selected the galaxies for being disturbed. So we don't have an unbiased sample to quantify things. This is just a study that opened the road to try to understand how we can pinpoint the different mechanisms. And this is actually what we have been doing, or we just started with Magnet, which is a new survey that really wants to give the definitive answer of the relative importance and effectiveness of the different mechanisms in the local universe. We are observing 65 square degrees with the H-alpha images, and this is a contiguous region that really includes all the different environment, excluding the clusters, because we know that in cluster ramp pressure stripping is very important. We really want to study the regions where the vast majority of the environments where the vast majority of galaxies are located. This is a very international collaboration. It's led by 4 people, myself included, and this is our S shape of the regions that we are observing. And so you can see that there are different filaments, the different colors refer to 2 different redshift bins. And we have groups, we have a variety of galaxies, and we really wanted to study this in an homogeneous way, unbiased way, capturing whatever there is, from normal star-forming galaxies to passive systems, to really be able to give a census of this. From the literature data that there are for now, there are about 450 galaxies with mass larger than 10 to the 9. We use the classification of groups from literature, and we have about 20 groups, and we identify the filaments with these pairs, and we didn't focus on voids yet. But obviously, with the upcoming observation, for example, from Foremost, 4HS, that will cover this field, we expect to have many more galaxies here. So the questions are really, what are the physical processes that dominate the galaxy transformation in the different environment? If we can distinguish between internal mechanisms and external mechanisms, try to characterize the time scale of star formation quenching, and really have a multi-wavelength view. We really think that we need to have, at the same time, optical, H1, X-ray information to really characterize, in general, what's going on. Since data are still taking, to start with, I started the work with theoretical prediction. So we use the semi-analytic model of Gaia to really see what simulation expect for galaxies in this environment. So we extracted boxes from the simulation of a region in the simulated volume that had a very similar environmental distribution than our observed field. And we started doing some measurements to provide some expectation. What we did is also, we tried to characterize the environmental history of this galaxy. So we tried to characterize the physical mechanisms since redshift 2. And so for each galaxy, we identified through the merger tree whether it underwent some mergers, some tidal interaction, if ramp pressure stripping is affecting, or starvation. Because we really want to understand how important is the entire history of the galaxy on the properties that we see today. So, for example, here there is the frequency of the different mechanisms in galaxies in the different environments. And according to simulations for typical fields in the galaxies, we have that actually the vast majority of the galaxy underwent at least a merger event since redshift 2. As expected, for example, ramp pressure is efficient only at the group level, sometimes at the filaments, And still, especially in isolation of these red galaxies, many galaxies underwent no physical mechanisms since redshift 2. So there is a non-negligible population that really didn't feel any environmental effect. Then we also studied, for example, how galaxies undergoing the different mechanisms in the different environment are distributed. And for example, regardless of the mechanisms, isolated galaxies are always at halo masses that are smaller than other galaxies. We see that filaments galaxies are always intermediate between pairs and groups. Filaments are really an heterogeneous population. And we see some slight differences depending on the physical mechanism affecting the galaxies, but still nothing is really predominant. We also measure quench fraction, and again, we see, for example, that even among isolated galaxies, we see that the quench fraction depends on stellar mass, and we do have a non-negligible quench fraction at low masses. So even galaxies in isolation quench for some reasons, which most likely are internal. And then we see that the highest quench fraction, independently on the mechanisms, are in groups, and this is consistent with what has been done in the past. And finally, and this is just a prediction, we also studied the color of the galaxy versus stellar mass for galaxies in a different environment and affected by different mechanisms. And here we would really like to put on our data points to see whether they follow the simulation or not. And we see, again, for example, that the fraction of galaxies which are red really depends both on the environment, so the different rows, but also in from the mechanisms. For example, run-pressure split galaxies which are red are typically less massive than galaxies that are red and underwent a tidal or a merger event. So there are many subtle dependencies, even though there seems to be a clear striking trends, suggesting again that it's very, very complicated to characterize environmental effects in the different physical processes. So, just to conclude, in general, clusters are really the most massive extreme environment in which galaxies can be found. They really affect the galaxy life, and in most of the cases, run pressure splitting is by far the strongest mechanism. So, to some extent, the understanding cluster environment nowadays is quite easy. We know what's going on. In general, though, there are many different physical mechanisms that affect the galaxies, and knowing the environment and looking at the spatial cell properties, we can get information on what was the mechanisms, even though it's not always so easy and so linear, also because in some cases there are multiple mechanisms affecting the same galaxies. So far, we do not have a coherent and clear census of the incidence of the different mechanisms that affect galaxy in the different environment. And to try to address this, we are starting this sample, this survey that's called Magnet, for which we really hope to get a complete understanding.
Thank you very much, Benedetta. Very nice talk. Questions?
One question. In the beginning, we saw that the spectra of the quench galaxies, the hydrogen lines are absorption.
Yes.
Why those absorption lines happen? I mean, if they are quenched, I don't expect to be hydrogen in the galaxy. So is that absorption coming from the path?
No, it's the spectra of the stars, A-type stars that form the galaxy, and the Balman lines in absorption. And so we see the signature. This means that there are many A-stars galaxies in the galaxy.
But that means there is hydrogen in those galaxies. They are just not forming.
But
stars.
It's in the atmosphere of the stars.
Yes.
Okay.
Okay.
So there are no hydrogen clumps.
No.
Okay.
No.
More questions? Carla?
Yes, I also, very nice talk, the way. So I also saw when you showed the news data that you have galaxies with some clumps. That clumps are from a star formation?
Yes.
Okay. So my question is, have you been testing the chemistry for the gas or other there can be signatures of your.
Yes, so we managed to study the ionized metallicity. And obviously, I mean, I have many results, I can talk of whatever you like. But what we study is both the metallicity in the galaxies, but especially in the tails of these galaxies.
Okay.
And what we see is that the metallicity in the tails has a gradient that it's very steep, and it's much steeper than the gradient that you see in the galaxy. So it's not just a continuation.
Okay.
And so the idea is that the gas strip, it mixes with the ICM before collapsing. So it mixes, it's collapsed, and so we have a fraction of the metallicity of the ICM, and this explains the stiffness.
Yeah. Interesting. Other elements have you been tested?
No, we started doing some chemical theoretical analysis, but the PhD student that was doing it left the field, and we have all that stuff instead. But in general, the problem is that we can do it only on the clamps, because in the diffuse, the signal is very low, and at the end, there are only 5 or 6 galaxies that really have long tails where we can actually see gradients and see a variation, because if the tail is small, with all the projection effects and things, it's very hard to distinguish what is in the galaxy and what it's out.
Okay, nice, thank you.
I have a question. Sorry. Okay.
One comment and a question. The comment is I loved the cartoons at the beginning.
Yeah,
Those were actually for someone who's for a stellar astronomer, those cartoons were super useful.
Right.
Magnificent way of for us to understand. So question which perhaps is very, very basic. In many cases you were showing maps of galaxies where you were, from my understanding, you could tell the star formation history pixel by pixel.
Yes.
How?
You do with a spectrophotometric code that actually models, finds the best combination of stars of different age that reproduces the spectrum. And so you can understand what was the star formation at different epochs at any given location.
All right. So okay. So basically you do a
You decompose
spectral fitting
Exactly.
pixel by pixel. Cool.
Exactly.
Okay, thanks.
I have a question. At the beginning, you showed the distribution of filaments from galaxies and dark matter, and there were some differences.
Yes.
Are those differences real, and why they?
Well, they are real. Well, that was obviously from the simulation, because the only thing we can do with dark matter. But the thing is that galaxies follow the dark matter, but there is a bias assembly, and so they do not track exactly the dark matter. There is some scatters in their distribution, so it's real. But probably it's also it's a limitation of the resolution and many things. So it's hard. It's not a systematic shift. It's random, because also the way disperse works. And so it's very hard to quantify and say, okay, let's correct of this percent the galaxy distribution to reproduce the dark matter.
Okay. And respect to the different mechanism in protocluster at high redshift, which is the mechanism that start the first to quench galaxies? Mergers or?
Yes, probably yes. We still do not have clear evidence of ramp pressure stripping at very high redshift. We are sure it happens around redshift 1, 1.5, even though one thing is saying that there is a case where we can detect ramp pressure, so it's there, but the other thing is to have a statistical sample to be able to say how efficient it is, and we don't have that. For sure, mergers are ongoing, and so I would say that for now, mergers are the things that we detect.
Okay. One question?
See, Sefka being Sefka, I cannot not ask about magnet. Given the
We try to get the JPass data, but we didn't manage.
All right.
From the
that
website.
is sort of what's going in that direction. So the obvious question is, you're not looking for magnetic fields.
Not yet.
All right. Oh,
I mean-
that comes interesting.
The idea is to really have all the different wavelengths and all the different components in clusters for the ramp. I'm sorry, I didn't let you finish the question.
So it was a series of questions. One was, but the name magnet sort
I
of
know.
hints towards magnetic fields. Then the obvious questions are how big, maybe you mentioned that I missed it, how big is the area? And
65 square degrees.
65 square degrees. And sorry, from SAFECA point of view, 65 square degrees is small. How deep? Is H alpha, right?
It's H alpha. We have 1,300 hours with VST. We expect to go down to stellar massive 10 to the 8.
Magnitude?
I can check it.
Sorry.
Sorry.
Thanks.
I have it.
Because the obvious thing would be to compare with
Yes.
J pass or J plus, right?
Yeah, it would be great to have, yes, us to have the different magnitudes and things. Yeah.
What is the exposure time in DSP?
So this is large program, and we finished the first year, and they are not observing as much as we wanted, and we have 10 square degrees for now. The hope is to finish in the next 2 or 3 years. In the meantime, we've been trying to have meerkat data. We went for a large program for twice, and they didn't give us time. Now we are trying to start with the smaller samples, because we really want to the H1 to really see what's going on, and we really want to have the continuous area to really see whether there are some H1 clouds in between galaxies, because targeting galaxy by galaxy, you miss what's in between, and so you don't know exactly what's going on.
More questions? No? Let's think again in a minute. Yeah, it's me.